Hello, everybody. It's great to be, remotely with you. So today I'm going to share some of our recent insights into a novel class of graph databases that we call neural graph databases that I've been working on together with a bunch of other people from SPCL in the last year. So a very brief overview. In my research, I'm interested in different types of sparse graph computations, ranging from graph neural networks, graph streaming, graph databases, which is going to be topic for today, classical graph algorithms, graph mining, and a bunch of others, how to run them, but also how to run them efficiently on different hardware resources that we have these days, ranging from different heterogeneous resources up to different massively parallel settings. Before we start with graph databases, let's take a look at graphs in the first place. I don't think I have to convince people in the room that this is something very important, but let's go through it very briefly. We all know that we use graphs in social sciences, in engineering, biology, chemistry, and a plethora of other domains, which makes them something that we really care about. But we do have many challenges there, right? So some of them are as follows. The graph data sets that we deal with are huge. They are quite irregular because vertices may have wildly varying numbers of neighbors. Their computations on these graph data sets are communication and synchronization heavy, which also makes them implicitly power hungry. And usually the problems we deal with have very high time complexities. Problems are very hard also in the classical computational complexity sense. Today we are going to speak about graph databases. So on the picture, we can see a plain graph, a model used in different types of graph computations. In graph databases, and one of the established models that models that we use is labeled property graph, where arbitrary vertices and edges can have attached sets of labels, which are kind of the classes of these entities, as well as properties which are basically arbitrary key value pairs. Right. So this makes the data model very complicated. And in reality, these graph data sets, because of having these additional data, these additional labels and properties, can easily grow by more than 10x. Right. So here we can see an example data set in the labeled property graph. So the blue parts are the dark blue parts are the vertices, the light blue are the edges. They have their own associated different types of labels. So this graph, as you probably imagine, models different types of papers, reports, and their citations, right? And the green parts are the properties, such as titles, number of authors, equations in the paper, etc., etc. Right? So it's just to convince you that this is very complex, and but we do care about it because yes, graph databases are one of the key technologies that we've been developing these days. At the same time, in the last couple of years, we've seen an explosion of works related to running different machine learning algorithms on graph datasets. Right? So this is one of the key, and actually these days, the most important mechanisms that's being used for the so-called graph representation learning is so-called graph neural networks. So there are some very big recent success stories of graph neural networks, in short, GNNs. One of them is basically using GNNs to develop placement methodology for very fast chip design, work that did a lot of stir in like a year ago. And one of the key mechanisms they use for their approach in Google is basically to use a class of graph neural networks called graph attention network. Then the other very highly successful recent story is the AlphaFold model, which is basically how to predict the protein structure based on its amino acid sequence. And again, they are using graph neural networks as one of the power forces behind the whole model. Then there are tons of other different schemes, just ranging from learning to simulate complex physics with GNNs up to even proving novel mathematical theories. Right? So basically, we know that we would like to use them, and the question is, how do we use them for more powerful graph databases? So plan for today is that we'll first take a look at how to combine the power of GNNs with graph databases at the data model level. And then we'll take a very brief look, like a very brief summary at some of our recent insights into how to scale them to really big scales, ranging to hundreds of thousands of cores. So in general, let's take a look at like a very brief summary at how deep learning work in general. So we have some input samples, and we are using these samples, for example, the picture of the cat, to train our neural network. Right? So we are learning we are using the sample to evaluate its value on this neural network. We are obtaining some output values, some predictions. We are comparing them to the ground truth. We are backpropagating. In the process, we are updating the weights. And we are, as a matter of fact, we are learning some heuristic, right, to give us these predictions. Now in GNNs, pipeline is very similar, with the main difference is that the input samples are now a graph, right? So this could still be some photos, but now we need to consider explicitly the fact that they have some relationships between them, right? And these relationships are something that makes efficient processing of GNNs really much more complicated than what we have in traditional deep learning. So here we can see again a single input sample of the GNN pipeline. So it's a vertex that can model like a photo or a person or anything else. It's always having some additional some compounding feature vector, right? So the feature vector is some vector that encodes the semantics of a given task. So it could be, for example, the positions of some protein molecules in the three-dimensional space, or something completely arbitrary that's relevant for our task. Right, we can see these dependencies coming from this vertex to some other vertices. And now at a very high level in GNNs, we have these input samples. We have stacked them here. They can form, for example, a mini batch or a full batch. This can be our whole graph stacked in this way. And then we are feeding these input samples into a series of GNN layers in which we first use a so-called graph-related operation. For example, graph convolution, in which we are, for every vertex, we are grabbing the neighboring vertices and we are fetching the feature vectors and doing, for example, summation or averaging or doing some other operation like this. Just basically you can think about it as a sort of PageRank on steroids. So because we are using something more complex than just single scalar values. Then we are feeding this into a dense operation in the same GNN layer, which is usually some neural network operation, for example, MLP, or maybe just a plain linear projection, or something more complicated. And at the end, we are feeding this into ReLU, which is some optional nonlinearity. And then we repeat this, right? So this is a single GNN layer. We repeat it many times as we need. Right. So now, how do we actually use these GNNs together with graph databases? So our main idea was to combine this at the level of the data model. So how to basically encode this LPG data set so that we could feed this into arbitrary GNN pipeline and obtain the predictions. Here we can see, for this we developed something we call LPG2VEC, which is an encoder that translates the LPG graph datasets into the form digestible to arbitrary GNN pipeline. Here we can see again our LPG graph with the labels, with the properties, and what we are doing in LPG2VEC is something very simple. We are encoding different types of these labels and properties into basically input feature vectors, right? So for example, if we have a paper network with our abstracts, we are using a transformer to encode it to some, or something as simple as one-hot encoding to encode it to some feature vector. The same for vertex labels. We apply some simple discretization, for example, to different properties, or just one-hot encoding to the labels, obtaining feature vectors that are really dependent on the data that we are currently encoding, right? And we are concatenating all these things to create the vectors that we are then using in combination with the plane graph structure. And this basically can be fed directly into different GNN pipelines to obtain further predictions for the LPG graphs. Some example results. Here we can see two plots. On the left plot, we can see a small variant of the Microsoft Knowledge Academic graph. On the right side, we can see a big graph. And each point on the x-axis is related to a different graph neural network model. So GCN stands for graph convolutional network, GAT stands for graph attention network, GIN stands for graph isomorphism network. And the y-axis is the test accuracy, so the higher, the better. And really the purpose of these plots is to show that with LPG2VEC, we can have better accuracy because LPG2VEC successfully preserves this additional information that we have in LPG graphs on top of the graph structure to make better predictions. So that's why in the data series, we can see different shades of blue, and the lightest one is basically none, which means that this is just pure graph structure without any labels and without any properties. Then we have progressively darker blue colors corresponding to the graph where we use the labels. The properties. In that case, it's just a title, and then a combination of both the labels and the title property from the graph dataset. In our paper, we are doing much more detailed analysis with basically different, like dozens of different properties, and like adding them progressively one by one. And we can see that with the more data we incorporate, the better the prediction, which is not really surprising, because of course, if you get more information, if you get more data, it's usually that you are going to get some better accuracy or better prediction. But what's very nice is that actually LPG2VEC successfully preserves this information, right? So we can use it with our encoding schemes to actually get better accuracy. Similar results for node regression tasks. So here we are using Neo4j datasets that we obtained from the internet. Here, the lower the better, because we have test MAE here. And again, the more stuff we encode in LPG2VEC, the better the accuracy, because the lower the error is, with some outliers like here. We have much more results in the paper that was published last year at the conference called Learning on Graphs, where we also analyze correlations between different types of properties. So go ahead and check it if you would like to know more details. Now some very, very brief, the summary about this part. So LPG2VEC is our main outcome here, that is an encoder for enabling feeding arbitrary LPG graph datasets into different GNN processing pipelines, which really establishes the foundations, like the very first step towards something we call neural graph databases. But what about the performance, system design, all these other things, right? And for this, let's have a look at the very brief summary at our other recent science in this domain. So in step one, what we did was to try to understand, to get better performance for neural graph databases, we need to understand better parallel processing of GNNs themselves, right? And for this, we developed a taxonomy of parallelism and distribution that we used to develop several novel classes of attentional graph neural networks. So these are quite powerful models used, for example, in the AlphaFold scheme. And we use this taxonomy to make better versions of these models that scale to large numbers of graph vertices and edges. In our taxonomy, we, on one hand, try to understand the parallelization of both data aspects, so how to parallelize the processing of the pipeline by parallelizing the processing of the samples. And here we identify a bunch of variants, such as graph partition parallelism or mini-batch parallelism, but also the model parallelism, so how to parallelize the whole part on the right side, which is really the pipeline of the model itself. And here we identify also different opportunities for parallelization, things like operator parallelism, pipeline, and artificial neural network parallelism. Again, all the details are in the papers. I'm not sure if we have much more time, but if we do, I will just have two more slides about something more graph database related, namely system design and implementation. Because once we understand the parallelism, we of course have a lot of other things like the actual graph database design, which is like ACID properties and the data model itself, how to implement it in the distributed setting. And for this, we developed something that we call GDI, which stands for a Graph Database Interface Standard, which is really a way to identify and implement in a high-performance way building blocks for different graph databases running on distributed memory machines. And GDI, in a very short, consists of two parts, of the GDI specification and the GDI implementation. The GDI specification is a long specification of which is our final result of the process in which we identified and crystallized performance-critical building blocks of the design of graph databases into a portable and productive API. That's basically the API for the data access and transactional layers. And then we separate the API from the specification, from the implementation, to ensure, on one hand, productivity, on the other hand, portability. So the specification itself is fully independent of any architecture underneath. And then in the implementation, we use RDMA, the fully offloaded RDMA operations, and tuned MPI collectives for high performance. Right? And to it, we're able to scale our graph database design to a very large scale, using basically full scale of the P-Stain supercomputer, running our system on more than 100,000 compute cores, which corresponds to more than 7,000 compute servers. We have some results for the OLAP workloads. Here we can see on the x-axis scaling of number of Earth servers up to 7,142, together with scaling of the graphs that we are using. So the largest ones have nearly 300 billion edges. And the different data series correspond to different algorithms, such as PageRank, connected components, or some others. And you can see that we scale the design pretty well. So the runtime is of course increasing, but again, we are running this for the bigger and the bigger graph, right? So we do scale to these very large numbers. And to the best of our knowledge, this is the largest published result in the domain of graph databases so far, in terms of the number of used compute cores and other hardware resources. We also have such results for the OLTP workloads with different types of queries like modifying vertices, reading vertices, and some others. Again, all the details are in the paper. With the slide, I'd like to conclude, and I will be taking any questions.
Okay.
I have a quick question. You just stated, how does it compare to DGL?
How is it compared to DGL is the question.
Oh, DGL is a framework that is really focusing on the GNN computations for mostly static graphs, right? So they don't really do graph database transactions, graph database properties, and stuff like that.
Yeah, okay, thank you.
Okay.
I mean, basically, just one more comment to make it full. One other so the first part of the talk, which is basically LPG2VEC, is you can basically use LPG2VEC to process your LPG graphs that you have together with with DGL, because basically what you can do, you can take your LPG graph that you have, you can run it through LPG2VEC, and the outcome of it you can just feed directly into DGL or this DGL if you prefer distributed version, right? So this was kind of like the purpose of that part was to have a bridge between the world of graph databases at this point and a plethora of different frameworks and pipelines you have in the GNN world. But on the other hand, DGL itself will not act as a graph database. I mean, it doesn't have all these capabilities.
All right. Thanks again for the talk.
Thanks a lot.
Yeah. Up next is Longbin.
Actually, I have another question. Sorry.
Yeah.
Go ahead. Go ahead. Go ahead.
Yeah, yeah.
Okay. So I have a question, because I think you for the GNN part is necessary with how the property graph schema is designed. So in this way, for example, like in the previous talk, someone mentioned that everyone in a parliament is a male. If we put a male as a property, maybe the GNN may perform in a way, but if we like treat male as a vertex, we can see every node connect to that vertex, and in this way, the GNN may behave strangely. So I mean, in practice, how does the schema design of a graph database like affects the output of GNN or the performance of GNN, and how can we deal with that?
I'm not sure if I got the question fully. So you're asking what happens if, for example, we have some graph modification, and then how does it impact the GNN running, or what was again the question? Sorry, I didn't.
Oh, sorry. I mean, because like we can like have a property graph, and we treat the gender of a person as a separate labeled vertex.
Yes.
Yeah.
Yes.
Maybe we only got two different labels. Two different gender vertices there, maybe male and
yes.
female. We can see a large number of person will connect to one
yes.
and the other two female.
Oh, I see. And then you're asking how would it work for GNN? So yeah. I mean, so this I would say this really depends on how you structure the data, right? So if you choose to have your data structured in such a way that you have, let's say, one huge vertex, which really is like basically a label vertex that is kind of connected at the structural level to, let's say, all other vertices because it's like a male or a female, or then, I mean, you need to make sure that this is not something that the GNN will see, in a sense that you don't want, let's say that you are a doctor, you want to predict what is the probability for people having some condition, right? Just to like make better decisions as a doctor. And then of course you may have this vertex, but then you don't want to run these predictions for the vertex that models like gender, right? So in that case, you would need to make sure to actually not feed this vertex at the structural level to the LPG2VEC, because then it would basically act as, okay, this is some vertex I need to run the prediction for. You would need to make sure at the data conversion process that that these labels are being translated as the labels, not as a part of the graph.
Yeah. Then in this way, maybe the design of the database schema, like we have to bear in mind how the like GNN task would be, and
Yes.
and, yeah,
Yes.
that is
Yes.
maybe a little bit challenging for user. Like I already got a graph database. Yeah.
Yep. I mean, that's yes, this is like the first step, of course. And as you say, there are many different corner cases. Also, I mean, you can think about the same about RDF datasets, right? I mean, RDFs, you can also have the same issue. And basically this would correspond to, okay, having some part of some module that is going to translate this into the form that you want to learn for, right? Because yeah, this is, I mean, in any case, in GNNs, everything is kind of task driven, right? So you also always need to pay attention to train for a given task, right? So in that sense, you also have these issues in the GNN pipelines in the first place. I mean, not really issues, but features of like this is how they work. You need to train for a given task, right? So in that case, you need to pay attention to use the data in such a way that actually makes sense.
Okay.
But it's really also like a part of the whole learning and process in general, because that's how you build like deep learning pipelines in the first place.
Okay. Thank you.